Welcome to the lecture on control systems, modeling and finding the transfer function of physical systems. I am Dr. Purnima S., Assistant Professor from the Department of Applied Electronics and Instrumentation Engineering, Rajagiri School of Engineering and Technology. So, how do we get the mathematical modeling of a physical system? If it's an electrical system, we can write the Kirchhoff's laws to get the mathematical model. For an mechanical system, we can use Newton's laws for the same. Let us look at a mechanical system. A basic mechanical system can be modeled using three elements, namely mass, spring, and a dashpot. A mass represents the weight of the system. A spring represents the elasticity in the system, and the dashpot is used to represent the friction in the system. You might be familiar with a mass and a spring, but may not be that much familiar with a dashpot. So, what is a dashpot? It is typically found in the shock absorbers in cars. Basically, a hydraulic cylinder in the shock absorber is called a dashpot. It is modeled by using a cylinder and a piston arrangement. There are two types of mechanical systems, namely translational and rotational type. Let us look at the translational mechanical systems first. So, translational systems are mechanical systems which move in a straight line. Whenever a force is applied to this translational system, it is opposed by opposing forces due to mass, elasticity, and friction of the system. So basically, a mass, spring, and dashpot can be modeled, or the symbol used to represent mass, spring, and dashpot are as shown in figure. What are the symbols used? We have X used to represent the displacement, V used to represent the velocity, A for the acceleration, F for the applied force, and we have the opposing forces due to mass, spring, and dashpot represented by Fm, Fk, and Fb, where M, K, and B are the mass, the stiffness of the spring, and the viscous friction coefficient respectively. So, let us look at mass. So, mass is modeled as shown in figure. Here, F is the applied force acting on the body, and X is the corresponding displacement acting in the direction of the force. Here we assume that the mass is an ideal mass having negligible friction and negligible elasticity. So, the opposing force due to mass, Fm, is proportional to the acceleration of the body. So, removing the proportionality constant, we can write it as F is equal to m into A, where m is the mass. Acceleration can be represented in terms of displacement as d square x by dt square. Now, by applying the Newton's second law, let's see what will happen. By Newton's second law, we know that the sum of the applied forces will be equal to the sum of the opposing forces. So we can write it as F is equal to Fm, where F is the applied force and Fm is the opposing force. So the net equation will be F is equal to Fm equal to m into d square x by dt square. Let us look at the same modeling for the mass. For the spring, we consider an ideal spring with negligible friction and mass. This spring is applied by a force of F, and proportional to that we have a displacement of x. So the opposing force Fk is proportional to the displacement. Removing the proportionality, we have Fk is equal to k into x, where k is the stiffness of the spring. Now, applying Newton's second law, we have applied force is equal to opposing force is equal to K into X. We have the third element, which is the dashpot. Notice that all the all the components are connected to a fixed reference station. So here we have an ideal dashpot with negligible mass and elasticity being applied by a force of F. So the opposing force Fb is now proportional to the velocity in the system. So Fb is equal to B into V, where B is the viscous frictional coefficient of the dashpot. The velocity is expressed in terms of displacement as dx by dt. Applying Newton's second law, we have the applied force is equal to opposing force. Let us look at mathematical modeling and transfer function determination of translational systems. Let's look at the first problem. The question is to write the differential equations governing the mechanical systems shown in figure and also to determine the transfer function. So this is the system shown in figure. You have a spring K1 connected to mass M1, which is connected through a dashpot to mass M2. There is another spring connecting between mass M1 and M2. F is the applied force. B1 and B2 are the frictional coefficients from the surface acting on mass M1 and M2 respectively. Due to the applied force F, we have a displacement of x due to mass M2 and a displacement x1 due to mass M1. So let's see what are the steps to find the transfer function of the system. So the transfer function of the system is nothing but the Laplace transform of the output divided by Laplace transform of the input. So here we have the output as the net displacement x and the input as the applied force F. So the transfer function will be x of s by f of s. So what are the steps? The first step is to draw the free body diagram of the masses M1 and M2 and mark all the forces acting on the body. The second step is to apply Newton's second law. The third step is to convert the new force balance equation to the differential equation form. Then we find the Laplace transform of this differential equation form. And finally, we find the transfer function as Laplace transform of output divided by Laplace transform of input. Also notice here that M1 and M2 are the interconnection points between different components or different elements in the system. So the M1 and M2 can also be considered as nodes in the system. A node is a point which connects to two elements, which interconnects two elements. So here M1 and M2 are the nodes in the system. So first step, let us look at the free body diagram of M1. So see that M1 is acted upon by opposing forces due to mass M1, spring K1, dashpot B, spring K and dashpot and the surface friction B1. So applying Newton's second law, we have sum of opposing forces is equal to 0 because there is no applied force directly on mass M1. Converting into the differential equation form, we have M1 d square x1 by dt square plus k1 into x1 plus b into dx1 minus x by dt plus k x1 minus x plus b1 into dx1 by dt is equal to 0. So notice that when you write the force due to this dashpot, which is connected between mass M1 and M2, we consider not only the displacement due to M1 but also the displacement due to M2. So actually we consider the net displacement, that is displacement acted upon by displacement at mass M1 minus displacement at mass M2. It is the net displacement acted upon here. Similarly, for the spring K, which is connected between M1 and M2, the net displacement will be x1 minus x. For the dashpot, x1 minus x. So that is how we have x1 minus x here. Similarly, we look at free body diagram of M2. Notice that here we have applied force F and all the opposing forces shown here. So, applying Newton's second law, we have sum of opposing forces equal to applied force. Writing the differential equation form, we have equation number 2. Notice here also that this dashpot and spring, which is common to both, is having a net displacement. And when you're drawing the free body diagram of M2, the relative displacement is the displacement of M2 minus M1. So we consider M2 as the dominant case here. So the net displacement is displacement of M2 minus displacement of M1. Here also we consider the same. Now the next step is to find the Laplace transform of these two differential equations 1 and 2. So taking the Laplace transform, we have equation number 3 and equation number 4. Notice that for the second derivative, the Laplace equivalent is s square into x1 of s. For the first derivative, the Laplace equivalent is s into x1 of s. Now rearranging these two equations, we get the final equation of the transfer function x of s by f of s as shown in this equation. So the final solution is writing the differential equations and finding the transfer function.